Redox reactions. There are a few topics from the C6 syllabus that it would be good for you to revise before you do this topic. These are oxidation and reduction, balancing equations, and displacement reactions of metals. I will add a few links along with this upload that's related to those topics. At the end of this lesson, you should be able to define and explain oxidation and reduction in terms of a transfer of electrons as well as a change in the oxidation state. You should be able to construct reduction half equations and oxidation half equations. And once you're able to do so, you should be able to combine both of these half equations to create a balanced chemical equation. What is a redox reaction? A redox reaction is simply a reaction in which both oxidation and reduction are taking place. We can define oxidation and reduction in terms of the gain or loss of electrons. If a species loses electrons, it's considered to be oxidation. That species is said to be oxidized. And if it gains electrons, it's said to be reduced. This acronym can be used to remember when we have oxidation or reduction, that is oil rig. Oxidation is loss, reduction is gain of electrons. We could also define it in terms of the oxidation state. The oxidation state, or we could also say oxidation number, it gives us an idea of how many electrons were removed from or gained by an atom when it bonds with another atom. Elements which are uncombined have an oxidation number of 0, meaning they have neither gained nor lost any electrons. Here we have a magnesium atom. Now, metals tend to react by losing electrons. And if magnesium loses 2 electrons, it forms an ion with a 2+ charge. Since electrons are negatively charged, if we remove electrons, it would be like subtracting a negative number, or would be like adding, so the oxidation number would increase. Since magnesium was uncombined, it had an oxidation number of 0, but if we remove 2 electrons, then the oxidation number would increase. Chlorine is a nonmetal and would react by gaining electrons. Again, since electrons are negatively charged, if we add an electron, or if we're adding a negative number, it's as if we're subtracting or making the number smaller. So if each chlorine has an oxidation number of 0 and we add an electron, then the oxidation number would decrease. Oxygen is a nonmetal, and when it reacts, it does so by gaining 2 electrons. Both oxygen atoms gain 2 electrons, then we would gain 4 electrons overall, and oxygen would have a -2 charge. Using our number line once again, if an oxygen atom has an oxidation number of 0 and it gains 2 electrons, electrons are negative, so we're making it more negative, or we're making that number smaller. And this relationship shows that once the oxidation number is increasing, that means we must be losing electrons, and if the oxidation number is decreasing, we must be gaining electrons. So when we look at reactions later on in this video, if there is an increase in oxidation number, then we would know that we should be removing electrons, or if the oxidation number decreases, that means we must be gaining electrons. Our next objective is for us to write oxidation or reduction half equations. In order to do so, we will use these 4 steps. First, we balance the atoms in that equation except for hydrogen and oxygen. Once those atoms have been balanced, we would then balance oxygen by adding water molecules. We would then balance hydrogen by adding hydrogen ions. And finally, we would balance the charges by adding electrons. For our first example, we look at the reaction between magnesium and the zinc ions. For the reaction between magnesium and the zinc ions, this is a displacement reaction, and magnesium would replace zinc in the solution, forming magnesium ions, while zinc ions would form zinc metal solid. So magnesium would form magnesium ions, while zinc ions would form the zinc atoms. The first step says we should balance the atoms. We have a balanced equation here in both cases. So the next thing would be to either balance oxygen or hydrogen, which we don't have. So we can then go ahead and balance our charges. We need to add electrons to ensure that the charges are equal on both sides. Now, since electrons are negative, if we add electrons to the reactant side, we would have a negative charge on the reactant side and a positive on the product side. But if we add electrons to the product side, we would have the charges cancelling. 2 positive charges from the ion plus the 2 negative charges from the electrons would cancel and give us a charge of 0. So the reactant and the product side would now have balanced charges. We can do the same for the half equation with zinc. On the product side, zinc has an oxidation number of 0. So we would add electrons on the reactant side. So the positive charges of the ion would cancel the negative charges of the electron. Both sides would have a charge of 0, which is our oxidizing and which is our reducing half equation. Remember, reduction is a gain of electrons. So the reaction with zinc shows where zinc has gained electrons, and this would be our reduction half equation. And magnesium has lost electrons, so it is the oxidation half equation. Another way that we could have identified which half was being oxidized or reduced is by using the oxidation numbers. So for magnesium, the oxidation number increased from 0 to positive 2. That increase shows us that it is an oxidation. And for the reaction with zinc, zinc's oxidation number decreased from +2 to 0, indicating that it has been reduced. Let's now look at an example which actually has some oxygen and hydrogen present. This is the reaction between potassium permanganate and hydrogen peroxide. When potassium permanganate is reduced, it forms the colorless manganese 2+ ions. MnO4- forms Mn2+. Let's focus on this one first. The first step says we should balance all the atoms except for oxygen and hydrogen. Here we have 1 manganese ion on the reactant side and 1 on the product side, so that is balanced. Next we would need to balance the number of oxygens, and we do this by adding water. Since we have 4 oxygen atoms on the reactant side, we need to add enough water molecules to give us 4 oxygen atoms. Since each water molecule only has 1 oxygen, it means we need 4 water molecules. Now that oxygen is balanced, we need to balance hydrogen. If we have 4 water molecules, it means we have 8 hydrogen atoms, and to balance hydrogen, we add hydrogen ions. So we would add 8H plus. The final step is to balance the charges. In order to do that, we must know the oxidation number for each species. Oxygen is -2, hydrogen is +1 in both cases. Manganese would have an oxidation number of +7. How do we know this? In an ion, the sum of oxidation numbers for all the atoms must be equal to the charge on that ion. So, that ion is MnO4-, which means that the oxidation number for manganese, which we wouldn't have known, we'll call that X, plus the oxidation number for oxygen, which is -2, times 4, since we have 4 of them, would be equal to the charge on the ion, which is -1. X minus 8 is equal to -1. So if we solved for X, which is the oxidation number of manganese, it would be -1 plus 8. That gives us a +7. To balance the charges, we need to add some electrons. The difference between +7 and +2 is 5. So we know we're adding 5 electrons somewhere, but it has to go on the side that would make the charges balanced. If we put it on the reactant side, so it's going to be out here. If we add 5 electrons here, again, electrons are negatively charged. So -5 plus 7 would give us a +2. So the charges there would be balanced. We couldn't have put it on the product side because +2 minus 5, so that -5 from the electrons would have given us a -3. So that would not have been correct. Now this is our reduction half equation because we can see that 1, we added electrons to the manganese ion, or we can compare the oxidation numbers. If it was +7 on the reactant side and it dropped all the way to +2 on the product side, that means the oxidation number decreased, and that decrease in oxidation number is reduction. So this is our reduction half equation. Okay, let's write the half equation for hydrogen peroxide. When hydrogen peroxide reacts, it's going to break down to form oxygen. First thing would be to balance everything except hydrogen and oxygen, but we only have hydrogen and oxygen. So we'll move on to step 2, balance the oxygen. It's already balanced here on both sides of the equation. We have 2 oxygen atoms. Next, we need to balance the hydrogen, and we do this by adding hydrogen ions. On our reactant side, we have 2 hydrogens, so we would put 2 hydrogen ions. Next, you would need to balance the charges. Oxygen usually has an oxidation number of -2, with the exception of peroxides. Whenever there's a peroxide, oxygen actually has an oxidation number of -1. On the product side, oxygen is in its elemental state, so it's uncombined, has an oxidation number of 0. We now need to balance the charges. Since there are 2 oxygen atoms with an oxidation number of -2, overall on the reactant side, the charge that we're focusing on is a -2. So we need to add electrons to a side that would make the charges equal on both sides. If we add it to the reactant side, then we would have -4, while on the product side it's a 0. So the correct place to add our electrons would be on the product side, where we now have 0 plus -2 on our product side, -2 on our reactant side. And since the oxidation number for oxygen increased from -1 to 0, that for us to combine both half equations. First thing is to ensure that the number of electrons in both half equations are equal. This is similar to when you're solving a simultaneous equation. So you would multiply all the species in the reduction half equation by the number of electrons in the oxidation half equation, and we would multiply all the species in the oxidation half equation by the number of electrons in the reduction half equation. Now that's a lot of words. We'll see that in action shortly. Then once we have done so, we can add both half equations together. Now in adding them, we would cancel all the species that are similar on the reactant and product side. Those will just cancel out. And we would add whatever is on the reactant side stays on the reactant side. Whatever is on the product side stays on the product side. From our first example with magnesium and zinc, we already have both equations having the same number of electrons. The reduction half equation has the electrons on the reactant side, so that can cancel with the oxidation half equation where the electrons are on the product side. There's nothing else that's similar, so we can just add the equations. On the reactant side, we have magnesium plus zinc 2 plus, and on the product side we have magnesium 2 plus zinc, and that would be our combined equation. Once we get to this point as well, because we'd have already balanced all the elements from before, this would just represent the balanced equation. Usually would also end up with an ionic equation, so it would be a balanced ionic equation. The second example, we had potassium permanganate and hydrogen peroxide. Our reduction half equation had 5 electrons, while the oxidation half equation has 2 electrons. We would first have to ensure that both equations have the same number of electrons, and we do that by multiplying the reduction half equation, all of the species, by the number of electrons in the oxidation half equation, and we would multiply the oxidation half equation by the number of electrons in the reduction half equation. So all those words just meant that we would end up with 2 MnO4 plus 16 hydrogen ions plus 10 electrons to form 2 manganese 2 plus and 8 water molecules. And then the other equation would then be 5 hydrogen peroxide would produce 5 oxygen molecules plus 10 hydrogen ions plus 10 electrons. Okay, we would then go ahead and cancel. On the reactant side of the reduction half equation, we have 10 electrons and we have 10 on the product side. We also have 10 electrons on the product side for the oxidation half equation, and we have 16 on the reactant side for the other equation, so we can actually just cancel 10 of them. We would be left with 6. We don't have any other species that's similar, so we would go ahead and add whatever is on the reactant side. We write them back. So we have MnO4 minus plus 6H plus 5 peroxide would form 2Mn2 plus 5 oxygen plus 8 water. Let's try some past paper questions. This question says, when sulfur dioxide is bubbled through acidified potassium chromate 6, the reaction which occurs can be represented by the following half equations. Write the balanced ionic equation for the reaction that occurs. Now we already have balanced half equations. We would then have to just add both equations together. To do so, we have to ensure the number of electrons are the same. We have 2 electrons here, 6 there, so we'll have to multiply all the species in this first equation by 6 and everything in the second by 2. We would then have 2 chromate ions, 12 electrons, 28 hydrogen ions, 4 chromium ions, and 14 water molecules. We would have up here 6 sulfur dioxide, 12 water molecules, 6 sulfate ions, 12 electrons, and 24 hydrogen ions. We could then go through and cancel all that similar. We have 12 water molecules on the reactant side here and 14 down here. So we would cancel and have only 2 water molecules remaining. 12 electrons can cancel. We have 24 hydrogen ions here, 28 down here, so we'd cancel and leave only 4. Since nothing else is similar, we could go ahead and add both equations. So it would be 6 sulfur dioxide plus 2 dichromate plus 4 hydrogen ions would produce 6 sulfate ions plus 4 chromium ions and 2 water molecules. And that would be it. State the change in oxidation number in any one identified reagent in the reaction. So to do that, you can either just pick one. So you could work out the oxidation number for sulfur in the first equation or chromium in the second. Chromium would be much easier because whenever you have numbers in bracket beside the name, it tells you the oxidation number. So this is saying that on the reaction side, that potassium dichromate or potassium chromate had an oxidation number of 6. And then on the product side, we see it has an oxidation number of 3. So the potassium dichromate 6 had chromium changing from +6 to +3. Another example, another past paper question. Hydrogen peroxide can act as both an oxidizing agent and a reducing agent, and chloric 1 and hypochloric acid can act as an oxidizing agent. Use appropriate half equations from those above to write a balanced equation to show the reaction between hydrogen peroxide and chloric 1 or hypochlorous acid. We would of course need the equation where we would of course need the reaction with hypochlorous acid, and we can see from this equation that it is gaining electrons. So we would need to select an equation where hydrogen peroxide is losing electrons. Remember, for a redox reaction, something must be oxidized and something must be reduced. So if hypochlorous acid is gaining electrons and it's being reduced, then we could not select an equation where the peroxide is also gaining electrons and also being reduced. We would have to select the one where it is losing electrons. Now, for this to make sense, we would have to reverse this equation. So it would be H2O2 forms O2, 2H plus 2 electrons. We would then go ahead and combine these 2 electrons by first multiplying this equation by 2 to ensure the number of electrons are equal, and that would give us 2 HOCl plus 2 hydrogen ions plus 2 electrons would form a chlorine molecule. 2 times a half is 1, plus 2 water molecules. We could go ahead and cancel. We have 2 hydrogens, 2 electrons, nothing else is similar, so we would add and get H2O2 plus 2 HOCl forms Cl2 plus O2 plus 2H2O. To answer the second question, you would work out your oxidation numbers, compare the reactant to product side again to see if we have an increase or a decrease in that number, and then you can tell what is oxidized and what is reduced. Thiosulfate ions are oxidized by iodine according to the following half equation. Write the half equation for the reduction of iodine, meaning that iodine will be gaining electrons. When iodine is diatomic, and when it gains electrons, it's going to form the ion. There are 2 atoms in this molecule, so it would form 2 ions, and in order for the charges to be equal, since we have 2 of them, then overall that would have been 2 negative charges. That means you would be adding 2 electrons. We should write the balanced equation for the reaction between the thiosulfate and iodine, and we will do what we have been doing before. We're going to ensure the number of electrons are the same. Then we can combine both, cancelling what is similar on either side. So we have 2 electrons on our reactant side here, 2 on the product side, so those can cancel. Nothing else is similar. So we would rewrite the remaining species as our balanced equation. That would be 2 thiosulfate ions plus iodine, and that would form SO4 plus 2I minus. And that is it. That's it. So from this video, what you should have learned was how we can define oxidation and reduction in terms of gain or loss of electrons. Oxidation is a loss of electrons, that's the oil from oil rig, and the rig means reduction is a gain of electrons. And we can also define it in terms of the oxidation number. If the oxidation number increases, that signifies that electrons were lost, so that's an oxidation. And if the oxidation number decreases, that signifies that electrons were gained, so that's a reduction. You should also know how to write and balance half equations. We would first balance the number of atoms, then balance the number of oxygens, then the number of hydrogens, and then balance the charges. And finally, to combine both half equations, we would ensure the number of electrons are the same in both, cancel like species, and then we add the remaining species. That's all for this topic. If you have any questions, please start a discussion in the WhatsApp group so that we can continue discussing it there.